Welcome to the video lecture for Chapter 1, Section 3. This is for college algebra, and my name is Jorge Gavillan. So, in Section 1.3, we're going to be doing adding, subtracting, multiplying, and dividing complex numbers. We're also going to solve quadratic equations in the complex number system. So, the first thing we're going to define is the imaginary unit, which is denoted by I, the letter I. This is a number whose square is -1. So, in other words, I squared is equal to -1. Now, complex numbers are numbers that are in the form of a plus bi, where a and b are real numbers. The real part, or the real number a, is called the real part of the number, and then b is called the imaginary part of the number a plus bi, where I, of course, is the imaginary unit, and I squared equals -1. So let's go ahead and add, subtract, multiply, and divide complex numbers. So equality of complex numbers. If a plus bi is equal to c plus di, if and only if a is equal to c and b is equal to d. So the sum of complex numbers. And so when you're adding complex numbers, so if I'm adding a plus bi plus c plus di, that is going to be equal to a plus c plus b plus d, and then the I. So in other words, what you do is you add component-wise. So you add the real numbers and then you add the imaginary part of the complex number. So the difference is the same way. So a plus bi minus c plus di is a minus c plus b minus d, and then the I. So here's an example. So for a, I have 3 plus 5i plus -2 plus 3i. And so therefore the first thing I do is I do 3 plus -2, and then I do 5. In essence, I'm doing 5i plus 3i. So then I end up with 1 plus 8i. And then for b, we have 6 plus 4i minus 3 plus 6i. And then so we end up with 6 minus 3, which is 3, and then 4 minus 6, which is -2. So the final answer is 3 minus 2i. And then here, multiplying complex numbers. So we have 5 plus 3i times 2 plus 7i. So one way that they do it a little differently here. We can just simply do FOIL. In other words, I can do 5 times 2 and then 5 times 7i, and then 3i times 2 and then 3i times 7i. Now the way they did it, you get the same result, but there's two different ways of you doing it. So the way they did it, they did distributive property. So then they end up with 10 plus 35i. That is the 5 times the 2 plus 7i. And then for the second part, they end up with 6i plus 21i squared, which is 3i times 2 and then 3i times 7i, which is 21i squared. Now, as we were told at the beginning of this lecture, I squared is equal to -1. So then therefore we end up with 10 plus 41i plus 21 times -1, which then ends up being -11 plus 41i. Now the product of complex numbers. So a plus bi times c plus di is simply a times c minus b times d, plus a times d plus b times c, and then the I. Now, if z is a complex number, so if z is equal to a plus bi is a complex number, then its conjugate, denoted by z bar, is defined as z bar is equal to a plus bi bar, which is then equal to a minus bi. So multiplying a complex number by its conjugate. So we're going to find the product of complex number z, which is 3 plus 4i, and its conjugate, which is z bar. And so z bar is simply 3 minus 4i. So z times z bar is going to be equal to 3 plus 4i, in this case, times 3 minus 4i, which then gives us 9 minus 12i plus 12i minus 16i squared, which then results in 9 plus 16, which is 25. So just one thing about this, when we multiply complex number times conjugate, the result is a real number. So the product of a complex number and its conjugate is a non-negative real number. That is, if z is equal to a plus bi, then z times z bar is simply a squared plus b squared. So here we're going to write the quotient of two complex numbers in standard form. So we're going to write each of the following in standard form. Standard form is a plus bi. So we have 1 plus 4i divided by 5 minus 12i for a. And then for b, we have 2 minus 3i divided by 4 minus 3i. So for a, as you can see, what we do is we multiply the top and the bottom by the conjugate of the denominator, which happens to be 5 plus 12i. So we do FOIL in the numerator and also FOIL in the denominator. Now, of course, the denominator will be a non-negative real number since that is what the rule is. So if I do z times z bar, in this case z is 5 minus 12i, z bar is 5 plus 12i, then I end up with 5 squared plus 12 squared, which is 25 plus 144, which is 169. That becomes my denominator. In the numerator, I just go ahead and multiply it out and combine like terms. So I end up with negative 43 plus 32i. And then in order for it to be in standard form, it has to be in the form of a plus bi. And so we separate the fraction into negative 43 over 169 plus 32 over 169i. And then for b, the same thing. We multiply the top and the bottom by the conjugate of the denominator, which happens to be 4 plus 3i. So therefore, our denominator becomes 4 squared plus 3 squared, which is 16 plus 9, which is 25. Our numerator, we go ahead and multiply everything out, and therefore we end up with 17 minus 6i. And then we have to separate that because it has to be in standard form. And a is 17 over 25 minus the bi, which in this case happens to be 6 over 25. So here's a theorem. The conjugate of a real number is the real number itself. So the conjugate of a complex number is the complex number itself. So z bar bar, in other words, is simply just the original complex number. Now the conjugate of the sum of two complex numbers equals the sum of their conjugates. So in other words, if I have z plus w bar, that is simply equal to z bar plus w bar. Now the conjugate of a product of two complex numbers equals the product of the conjugate. So z times w bar is equal to z bar times w bar. So the powers of I, and this is it's helpful, especially if you start multiplying, you get an exponent that's not a square. And so I to the first power is simply I squared is negative 1. I to the third, which is simply equal to I squared times I, happens to be negative 1 times I, which is negative I. And then I to the fourth is simply I squared times I squared, which is simply negative 1 times negative 1, which is equal to 1. And then what happens is that you can see the pattern repeat itself. So first we start with I, and then negative 1, then negative I, and then 1, and that pattern repeats in every fourth. So I to the fifth is equal to just I to the sixth is equal to I squared, I to the seventh is the same as I to the third, and I to the eighth is the same as I to the fourth. So evaluating powers of I. So I to the 27th is just simply equal to I to the 24th times I to the third. Now I to the 24th, we can simply separate that more into I to the fourth raised to the sixth power times I to the third. Now I to the fourth just simply becomes 1 to the sixth power, which is 1, and then I to the third power is negative I. And then b, I to the 101st power is equal to I raised to the 100th power times I to the first power, which then I to the first power is simply I. Now I to the fourth, we know that it just happens to be 1, so it's 1 to the 25th. So 1 to the 25th times I just simply becomes I. So we're going to solve quadratic equations in the complex number system. So if n is a positive real number, we define the printable square root of negative n, denoted by the square root of negative n, as being equal to the square root of n I, where I again is the imaginary unit and I squared is equal to negative 1. So let's solve these equations. We're going to solve each equation in a complex number system. So we have a, which is x squared is equal to 4, and then b, which is x squared is equal to negative 9. So a, x squared is equal to 4. We just take the square root of both sides. So x is equal to plus or minus 2. So this equation has two solutions, plus or minus 2. And in b, we have x squared is equal to negative 9. We take the square root of both sides. So we end up with x is equal to plus or minus square root of negative 9, which is equal to plus or minus square root of 9 times I. So in other words, we take that negative 1, we take it out, it becomes the square root of negative 1, which is simply just I, and the final answer is plus or minus 3I. So the quadratic formula in the complex number system, the solutions of quadratic equations, ax squared plus bx plus c is equal to 0, where a, b, and c are real numbers. A does not equal 0, are given by the following formula. So x is equal to negative b plus or minus square root of b squared minus 4ac over 2a. So the first thing, when we have a quadratic equation, we're going to solve it, and so we have to find what a, b, and c are in the given equation. So in this case, A is equal to 1, B is equal to -4, and then C is equal to 8. So the first thing we do is we find the value of the discriminant, sorry, and that's equal to -16. And so therefore we know that we don't have a real solution, but we do have a complex solution. So using equation 9, which just happens to be the quadratic equation, we plug in those values into our formula, and then we end up with 4 plus or minus square root of 16i over 2. We reduce that further to 4 plus or minus 4i over 2. We can go ahead and take out a 2, so we can cancel out a 2 in the numerator and the denominator. So then our final answer is 2 plus or minus 2i. So the two solutions would be 2 minus 2i and then 2 plus 2i. We check both of these and they actually work out. So the discriminant of a quadratic equation still serves as a way to determine the character of the solutions. If the discriminant is greater than 0, we have two unequal real solutions. If it's equal to 0, it has a repeated real solution or double root. If it's less than 0, the equation has two complex solutions that are not real, and the solutions are conjugates of each other. And we saw that here where we get 2 minus 2i and then 2 plus 2i. Those are conjugates of each other. So here's an example. Let's determine the character of a solution of a quadratic equation. Without solving, determine the character of the solution. So we have A, B, and C. So here A, for the letter A, we have A is equal to 3, B is 4, and C is 5. So the discriminant in this case happens to be equal to -44. So the solutions are two complex numbers that are not real and are conjugates of each other. For letter B, we have A is 2, B is 4, and C is 1. The discriminant is equal to 8, so the solutions are two unequal real numbers. An example would be -3 and 4. And then for letter C, we have A is 9, B is -6, and C is 1, so the discriminant is equal to 0. So and this has a repeated real number, that is, it has a double root. So this has a solution, if we were to factor it, would be something like x plus 3 to the second power. We take the square root of both sides, so we got x plus 3 is equal to 0, so x is equal to -3. We don't repeat that, right? That's just a double root, if you will. And that's the end of section 1.3. Thank you.